Hello, my name is Thiago Gama Rodrigues, and today I will present my work called Cloudlets Activation Scheme for Scalable Mobile Edge Computing with Transmission Power Control and Virtual Machine Migration. This work was published in the IEEE Transaction on Computers, and it is a feature paper of the September 2018 issue. First, a brief background into my research. On the one hand, we have conventional cloud computing, where desktop computers connect and use powerful servers. Since the computers are using the resources of the servers to run their own local applications, it's like you have a powerful server inside your house. You don't have to worry about the limitations of the computer anymore, since you're actually using the resources located in the server. On the other hand, we have mobile devices, which are small, portable, and convenient, but also have many limitations, such as small battery, slow connection, slow processing power, and severe limitation in what kind of applications they can run locally. By combining the two of them, we have mobile cloud computing, where mobile devices connect and use powerful servers. Since the mobile devices utilize the resources of the servers to run their own applications, it's like you have a powerful server on your hands. You don't have to worry about the limitations of your devices anymore, and you can run heavy applications with many users. Mobile applications usually benefit from low latency and transparency, where the user does not know that he is actually using a, a remote server and thinks he's running our applications locally. This means higher quality experience for the user. However, in mobile cloud computing, the servers are too distant, which means a longer delay and a lower quality. This is where we have a paradigm called edge cloud computing, where mobile devices connect and use powerful servers in the edge called cloudlets. The servers here are near to the users, which means lower latency and shorter delays. This not only means a higher quality of experience for the users, but also help us alleviate the workload of centralized servers, which can now focus on heavier applications. As a side note, the servers in the edge cloud computer or cloudlets are located in the edge, and they are individually less powerful, but they are also higher in number. The service delay in edge cloud computing is the whole time it takes for a user test to be completed. This includes the communication delay between the cloudlet and the server, the processing delay that is the time that the server takes to complete the task sent by the user, and the migration delay in case we need to send data between two different cloudlets. In simple terms, we can say that tasks take longer to be finished if cloudlets are too busy. However, overload of cloudlets can be caused by user mobility. If users suddenly start moving together towards one single cloudlet and connect to it, that cloudlet is going to get overloaded and is going to take longer to finish its own tasks. Overload can also be caused by new users. If too many users join the systems, the servers will not be able to handle that much work and will be overloaded. Obviously, these overloaded scenarios are a bad configuration where we have slow service and low quality of experience. We can increase the user capacity by introducing more cloudlets to the system, but this is a very expensive solution since the operation cost is very high. The best solution here is to more efficiently use the existing resources without adding something new. By more efficiently using the cloudlets that we have, we can balance the workload and have a higher quality experience. Therefore, my solution is to balance the workload between cloudlets. As shown here by this example, we can change the transmission power level of the cloudlets and migrate virtual machines, which are the virtual images of the devices, between the cloudlets in order to balance the workload and making sure that no cloudlet is overloaded. My solution lowers delay and raises capacity, and also must consider mobility and new users to make sure that we can have a very smart reconfiguration that will guarantee us a fast service and a higher quality. However, this problem is too complex because it has too many variables, so I use artificial intelligence. The resulting solution is suboptimal, but still good, and reconfiguration can be done more quickly because of the low complexity of artificial intelligence. The main contribution of this paper is as follows. I create a mathematical model that considers the whole life of the user task. This includes communication with the cloudlet, processing of the task at the cloudlet, and task migration between cloudlets if necessary. The model also considers user mobility and arrival of new users to be more realistic and make sure that the configuration is more efficient. I also utilize particle swarm optimization, an artificial intelligence algorithm, to model and find the configuration that maximizes system capacity. This means because maximizing system capacity means more users served by less cloudlets, we have a higher resource efficiency. This slide shows the results of my proposal. As you can see here, for different applications with different demands, my proposal is able to serve twice as many users as conventional methods located in the literature. This is because the conventional methods usually only consider some part of the service delay, but not the whole thing. This focus on just part of the service delay is more simple and easier to implement, but it's also less realistic and less efficient, as shown by the results. Since my proposal can handle twice as many users, this means that I use the resources more efficiently, and service providers can have a cheaper cost to deliver to the users, and we have also a lower delay for the users. In summary, with edge cloud computing, there are no limits for mobile devices, because we can have a better access to processing, connection, and better resources. However, edge cloud computing is also unstable and unreliable due to its dynamic nature. My solution to this is to mathematically model the scenario and find parameters of the optimum configuration with artificial intelligence. The model considers the whole lifetime of the task, as well as mobility and new users. The final impact is a higher user capacity for the system without sacrificing quality of experience. The proposal can serve twice as many users as conventional methods, while still respecting maximum service delay, which means we have a minimum threshold of quality experience, but still serve more users than conventional methods.